Okay, hello everybody, good morning. Hope all of you are fine. So today we are going to continue with one new algorithm first of all, then as much as we have time we move forward. After today you don't have homeworks anymore, but you're supposed to think about your projects for this course. For students who has both courses of the reinforcement learning and Islam, they are allowed to work on same project with one title, but if it's like because in reinforcement learning we allow that you can work with two people. Then if you wanna like work then work same project for this course and that course, then the project should be quite big, because then it's like four people project for just one with one title. Because of that, you should be aware of that. But about the details of the project, I will post soon, so that you can start to do whatever you want to do, or my suggestion ideas that I will give you. After this chapter I discussed some open problems. Those can be your projects during the course. If you look, I mentioned multiple, like I think about 4 open problems. But in next chapter also we have an interesting topic, that for occupancy grid mapping, how we can solve it with, for example, artificial neural network or deep learning. If you are familiar with, you can move toward that title too. But if you are not familiar, of course, mathematical ways of the solving different problems in the topics that we studied would be very interesting to think how to, for example, do something to improve it, how to merge them, or give some kind of combination of sensor fusion to plan to localize or map the environment. Anyway, I will give you some suggestions, but also you can think yourself too. Of course, I know that the time is limited, and based on that time that you have, it should be sufficient to do project. Any question about anything? Okay, so let's start with the histogram filter today. Histogram filter is applicable for many different applications, especially in image processing. It's very famous to do some image processing task and machine robot vision. But here we are focusing on the robot localization. We want to see if there is any way to use a histogram filter on robot localization. We already know base filter, and now we want to see how what is the general concept of the histogram filter, and if it's possible to merge base filter and histogram filter together in order to be able to localize a robot. So the motivation is based on that, and let's see how it looks like. So first of all, in this chapter we will talk about the non-parametric filters, and we define what does it mean. Then we move quickly toward the histogram filter localization, and you expected after this chapter, a small chapter, to know how these concepts are working and how we can really bring the histogram filter to the game of the localization of the robot that we have here. So keep this in your mind, that we have localization problem and mapping problem. So during the course we usually try to split them, because they are kind of separate problem, although we have to solve them together. But to understand different algorithms, we are separating how localization is working, and when we are going to map it, how we can have mapping part and how we can merge them together. So basically the idea is generally like that. So in order to understand the course, we have some course of today, we have some definition that you should be careful to understand that. So first of all, we have posterior. Posterior is a probability of the assigning observation to groups of given the data. So when we are talking about the posterior, you should always think about that the data is given. And the data, groups of data is given. It means that like robot is moving in the environment and we have the observation and the data for the robot. On the other hand, we have prior, that it is like before collecting the data. So we haven't seen the data, and we call those scenarios as prior, basically. But for understanding it is like much easier. You can consider that then like robot is here and moves to the next. So first one can be prior, next one can be posterior state. So current state and next state, kind of like that. So this is very common to use it in Islam algorithms, prior and posterior. We're gonna also in some cases during course use it. So keep this in your mind to make sure that you understand the concepts. We have different non-parametric filters that they are basically our replacement for Gaussian techniques. So in Gaussian, as you know pretty well, we had the distribution and we were talking about the mean and covariance in order to localize everything. But now we want to change it kind of to non-parametric filters. We want to see whole game in different scenario. How and what does it mean? It is like we say we don't have fixed functional form of the posterior, such as Gaussian that I explained, and they approximately they kind of approximate the posteriors by a finite number of values, so that we kind of want to, instead of having one Gaussian distribution, have many number of values in order to say where the robot is. By explaining this, you may think, okay, how that can be happen if you have number of values in order to say where the robot is, that we're gonna see soon. We can kind of say, okay, if I'm localizing robot, I'm robot in this room and I want to localize myself, instead of talking about just Gaussian distribution, I can discretize the environment, whatever we're doing in many different techniques, and saying like, what is the probability of being here, what is the probability of being here, instead of having just one value to showing that we can split it. So based on that, if you want to define it, the non-parametric filters, we can say that they are like relying on decomposition of the state space. It means that we can kind of split the environment to many different probabilities instead of one. And Leo, press the button. And the values are usually based on the cumulative probability of the posterior density in compact subregion of the state space that says where the robot is. So, of course, these concepts will be more clear soon with seeing visually what is happening. We say some of the approximation of the state space and where the location of the robot is coming from by random sampling from the posterior distribution that we have based on the prior and posterior that I explained to you, and the number of these posterior and prior approximation can vary by the number of splitting or number of decompositions that we are doing. What does it mean? It means that, like, if I have this state space and I want to decompose the environment, how much I decompose it to smaller spaces, kind of you can think about grids. If I split it to smaller grids, I have higher accuracy, because instead of saying I am here, so moving to the next state can be one big step. I can split it to smaller states so that I can say I have higher accuracy on the prediction of the prior and posterior for my robot. So is it clear so far? To understand this better, you can have a look at this figure over here. That this is the decomposition of the environment, so that it looks like exactly a grid that you know. and you can see different probabilities, like darker black point over here is like high robot, most likely, for example, can be here, and less likely is here, based on the color that we have, that it is representing the amount of probability that robot is there. So we say decomposition techniques can be static and decomposition techniques can be dynamic. What does it mean? It means that I can say, okay, this is my status space and environment. I want to localize my robot. I split and decompose the environment to this static number of grids. Then I start to develop some algorithms, some techniques that today we are going to see based on histogram filter, how this is working. But on the other hand, what I can do this side. Instead of decomposing the environment for a static number of kind of small elements or small spaces, I can say I'm going to decompose it in dynamic way. What does it mean? It means that, so based on the probability distribution that I have, the area that I don't know, the probability, I can say, okay, this is like big space, hold this area, but these spaces that are smaller, and I have some ideas that what is the, how likely robot is there, I can make them more precise. How much I know more about the environment, I can make the grid sizes smaller, so that give more chances to more accurately say where the robot is. So this is dynamic technique of the decomposition. That we can specifically rely on the posterior distribution of the where the robot is and work with. But of course, working with dynamic maps and dynamic decomposition is harder than a static one. Today we are going to basically talk about the what happened? Today, basically, we are going to talk about the static one, but we can easily, with some challenge, with some considerations, also move to the dynamic one. Is it clear so far? Any question here? Because we're gonna now see how this is happening, how we can work on it. Also, I need to mention that, like the figure that you see in the right side for density tree, also one of the techniques that we can work to do that is density tree approach. That is famous. We can use different techniques, but density tree approach is also one technique that we can achieve it. So, and resolution of the what we want to, how we want to localize it, we can change it dynamically. So for non-parametric approaches, when I'm talking about non-parametric approaches, I mean that we are not talking about Gaussian distribution anymore. We are talking about kind of grid-based decomposition that we want to say the probability of each grid where the robot is. Okay. One of the technique is adaptive approach. So it adapts the number of parameters to represent the prior online in adaptive approach. Second approach is resource adaptive approach. That in resource adaptive approach, we say, okay, based on the resource that we have on the embedded system of the robot, that is like, if you wanna, basically, since we are talking about localization, you have limited amount of power that in online form you can construct a map, localize the robot location based on that. Especially on the embedded systems, we have resource adapted approach that the decomposition is based on the amount of power that we have. It can be statically defined at the beginning, or it can be dynamically based on the resource that can be allocated to process it. Like you can say, in online way, when robot is moving, you are going to localize it So your robot's processor is busy with calculations or something, then dynamically you can decrease the accuracy over there, make it bluish, but at least you can localize. It's not lagging. You can bluish, localization decrease, the accuracy decreases or increases dynamically based on the amount of processing power that you have available to do the calculations of, for example, grid construction. Maybe this is like more reasonable when we are talking 3D mapping and 3D cloud construction, then this concept is more understandable there because it's very costly over there. So it is known that this approach plays an important role in robotics and enables robots to make decisions in real time. Because if your robot is like humanoid robot or flying robot that is flying or walking, then if your threads are becoming busy to do the constructing the map and its LAN algorithm, the control part will be in problem. Lagging there is unacceptable. And due to deal with this problem, we can say, okay, like the priority of this thread is higher, whatever resources that you have, allocate to the second part of the algorithm that we have. Because if we have like, if we don't use the resource adaptive approach, then you will not be able to process the data in online form and construct your map, and you lose it if you have limited resource. But if you have dynamic, then you still can deal with this problem and have some inaccurate, but still you have localization of your robot in the environment. So now we are going to talk about directly histogram filter. Histogram filter also decomposes the state space into finitely many regions, and it represents the posterior by histogram. So how this is happening? First of all, let's have a definition with the histogram. A histogram assigns a single cumulative probability of each region for each region of the whole grid space that we have. So kind of with histogram filter, we want to bring the probability for each one of the regions that we decompose from our environment in order to be able to localize where the robot is. So one of the common techniques and best approach to do this is using base filter. It means that the concept of bringing the probability form of the histogram filter into the base, into the game of the localization is using the concept of base filters. So in order to do that, we should first discuss that. In discrete spaces, we had discrete base filter that we've already seen. If you remember, we were discussing about the base filter and said it is continuous. And we said if we put sigma in the equation, it is discretized, and we can say some of the probabilities, we can calculate it. You solve examples and homeworks by simply doing some of the probabilities. And that was almost discretization of the state space that we have. Okay, so this one we studied already. On the other hand, in the continuous state spaces, for example, histogram filter can be applied, but in order to again apply it, we should apply the discretization that is kind of similar concept of what we have here with discrete base filter. But it comes from the histogram filter technique itself. So based on that concept, we can say histogram filter decomposes the continuous state space to finitely many regions, that we have the new state space actually, and the idea is that we use we should be able to use the discrete base filter to apply what we want to do on it. So what does it mean? It means that let's say we have a region and the environment. So in that environment, can be split to range of xt. So if we show whole environment as xt, range of xt can be split, can be demonstrated as splitting the environment to small regions. For example, we can say x1t union of all the x1s to xkt's can represent whole my environment. So each small region that we are splitting, we can call them as x's and put some labels on it, like based on the region x1 in time t that we are seeing. You can look at the tails and consider these tails as each one of the x's, and whole the xt as the environment that we have. So I've noted some notes here for readability. The state of the robot position based on, although we have splitting decomposing the environment, since we have time t also, so we can consider that also it is representing where the robot is based on the time t, since we are bringing the probability into the game. But also range xt, as I mentioned, is representing the whole state space, and xk is whole environment at the end as state space, so end of the region that we have including there. Meanwhile, we are defining this and we decomposing the environment. We have some limitations. One of the limitations is saying that we should not have any intersection between these areas by default, because if we have intersection, it means that if they have overlap, then the calculation should be considered that too, because the probability of the being here or being here can affect each other if they have overlap. So because of that, basically we say the decomposition is like drawing a line and splitting into two areas, not having overlap on the regions. So this is the limitation that we say, okay, there should not be any common between xkt and xit, and of course the I should not be k, because otherwise it represents the same decomposed region. Is it clear? Okay. On the other hand, the union of the all should represent again the range of the xt that we discussed. So the we say if you do the decomposition, if the environment is not like square, or it is like circular, after the splitting, the range should represent the same environment. You should not drop anything in the environment. And this is kind of also challenging, especially if you have weird shapes, and there are different techniques also to do this. Like if you have this shape of the environment, then it's not like easy to grid it, because when you do gridding, then you may have this over there. So that says that you should not drop this part in the environment. And to do this, we have different algorithms, different techniques too, that decomposition based on triangular technique that you will be able to decompose this part. For example, you have this region over here. How to do that? There are some techniques and optimization techniques, and also variety of papers how to do that. For example, one of the most common ways how we can do that, again, decompose this area to small triangles. We can do this as smaller, so then we have small regions, and we can decompose it, and we can consider it and bring it into the game. So is it clear? Yeah, when we are talking about the environment like class, everything is easy. We can grid it easily. But in those environments that basically usually is like that, is a little bit challenging, that we need to know how to do that. Finally, if we consider these two limitations, it should be fine for our technique that we are working on. So we say decomposition of continuous state space for a multi-dimensional grid where each grid cell is defined as like this one can be shown here, that you can see we have a grid and we can say x1t, x2t, and we continue to xkt at the end. So we also have a concept here that is better to know. We say we have granularity of the decomposition, that we can control trade-off between accuracy and computational efficiency. That as we explained already, based on the amount of computational resource that we have, we can say, okay, it is granularity of the decomposition. That is kind of common concept to know in Islam techniques. But what are the steps? We want to directly move to see how the steps of the histogram filter is. The whole idea is simple. Some equations just we need to use in order to be able to do that. First of all, we say assign a uniform probability to each state xt within each region xkt as initial belief. So your robot is going to start in the environment. And we said, okay, already we decomposed the environment. Now, as initial state, we don't know where the robot is, right? So we should have initial belief where the robot is. So since we don't know, we consider that we don't know where the robot is, we can say, okay, let's have initial belief. That initial belief can be calculated by this simple equation over here, that probability of xt, where the location of the robot is, because we are talking about localization, so is the probability of kt over all the probabilities that we can have. It means that we have the volume of the region xk and looks like something like this, that we decompose the environment. Then each one of these points and the size shows the probability of where the robot is. Since the size of these circles all are same, we don't know where they are, and it's kind of they are with same probability where the robot is. So here is like putting some values in each one of the grid cells, how likely robot is there. And we want to, with playing this and changing this, in order to be able to localize the robot. These, of course, representing some numbers also. That in next slide, I think we have one example. Let's go. So the same thing that I explained, with each region, we can only maintain the weights for each region. And when we are also when I'm calling about the weights and we are talking about the weights, keep it in your mind that we are talking about the probability of where the robot is, the weights for each region. So weights is referring to where the where each one of those are. And if we don't know, we equally distribute it. It means that over here, let's say simply probability of the xt where the robot is can be defined by this to initialize my initial belief. We can say the probability of kt over all the size of the region that I have, the size of the xkt is like, since we have 25 grid cells here, 1 over 25 becomes 0.04, so that I can initialize my my initial belief looking like this. So simply in grid cell, you put values, the initial belief where the robot is. It means that how likely where the robot is, we don't know, same probabilities. Now we want to kind of find out how we can change these probabilities in order to say, okay, more likely robot is here. Increase the value of probability here and decrease the other ones. That finally sums up to 1. Clear? Now, what we need to do. As I mentioned to you, histogram filter is going to be applied on base filter. We want to use the concept of base filter. And in base filter, what we had? We had the prediction step, we had the correction step. In prediction step, we had the motion model, that robot is moving in the environment, and based on that movement, we were having predicted belief. And this predicted belief were coming from previous belief and the motion command. The poses given by previous pose and motion command that we ran. So this was one state. Multiplying by predict belief, the previous belief, we have the predicted belief. So now you can think yourself how we can merge this concept into histogram filter. We want to use it in histogram filter in decomposition based form, not Gaussian distribution anymore. On the other hand, for the correction what we've had, the belief of xt, new belief actually, were calculation of the predicted belief that were coming from prediction step based on the motion model and the observation. So the observation that we have is probability of the observation given by the robot pose. That is normalized, and we're giving me the predicted the belief that where the robot is. So motion command, observation based on the vision were giving me base filter. As recap, what we've done over here, we said that this integral of the belief can be written as discrete form, that we can simply replace it by sigmas of the probabilities that should be 1. And now we want to maintain this again and use it in the histogram filter. And if we want to have a look at the discrete base filter, you already did it and implemented also. So for all of the case, do this first step, predicted probability of the sum of the probabilities that we have. And then this is like the algorithmic form of the prediction step. And here we have the correction step, like eta, the probability of observation, given by observation times the predicted probability that comes from there. Exactly the algorithmic form of the discrete base filter that we have over there. So clear? Of course, must be clear for all of you. We've studied it many times and applied Kalman filter, extended Kalman filter, unextended Kalman filter on this technique. Now we want to bring histogram filter into the game. So in order to be able to do that, of course, we will have prediction step and correction step. At the prediction step, what we do? We want to calculate the predicted belief of the integral of the probability of the poses given by pose and motion command times the belief that we have. So what we can do is that we can write predicted. So we already know that, right? Knew it. Now we can write it as predicted belief of the xt that is equal to sum of the beliefs, the previous beliefs, and some weights. So kind of weighted belief of the where the robot was. And what is the weight over here? The weight is coming from the grid and the grid cells that we decompose based on the histogram filter concept. So if you remember, I said that we have weights and it represents the grid cells in previous slide. Let me go here. So, or here, doesn't matter. These weights, these are called as weights of how likely where the robot is. Now, those weights are coming into the game by replacing this part by weights and multiply them by exactly the same concept that we already have, the belief of the xt minus 1. So, is it clear for everybody? Base filter, we remove this part and replace it with weights. Weights are coming from decomposition of histogram filter that are indexed by time t and the ice grid cell, ice region that we have. okay, in order to be able to calculate predicted belief. But how these weights can come and mathematically calculated, we can say the predicted weights are some of the weights times the probability of xi and xj given by motion command that I have. It means that, so I'm going to run the motion command, and probability of the motion command that can be run on my technique that I have applied by weights, and sum of all of them represents my weight for the belief that I'm going to calculate the predicted belief. In Bayes filter, what we were saying, so robot is somewhere, motion command, we run the motion command, and based on that motion command, we are updating the predicted belief, right? And now that is coming from here, and that is coming from the grid cell that I have. So whole grid cell that I have, I apply the motion command, and that motion command changes the probabilities over there by this equation over here. How that is happening? That is happening looking like this, if you want to visually understand. So at the beginning, we had the circle sizes all same, right? Let's say we're running motion command like this from initial belief. So robot is moving like in this direction one step. If robot moves in this direction in one step, what happens most likely, if we calculate the prediction step, the grid cells should be shifted to the up left. What does it mean? It means that probabilities of these being here, location after here, will be decreased, and probability of robot being over here will be increased. And it makes sense. Like, wherever I am in the environment, if I move this step, more likely I'm over there, not there, right? Whole probabilities of the grid cell will be shifted to the left up. Wherever I am. It shows that in worst case, even if the robot is here, the probability of being in that cube is higher. Although maybe initially is here, but says more likely robot is here. And what happens if we continue that? So if we do one more step of going there, so again the probability will be shifted more likely. And let me say, wherever your robot is here, if you always run the command of up left, after 100 times, if there are no obstacles or something, certainly you are at the corner, right? If just running motion command, certainly wherever you are, you finally end up there. So this says the same concept of the histogram filter in first stage of the updating motion command. Just calculation of the grid cells and updating the weights of that weights are coming from the probabilities there from initial. If you want to write whole equation in one term, we can write its predicted belief of xt is equal to 2 times sigma I1 to n, J1 to n. That represents the decomposed grid cell there, and the weights of the JST minus 1 times the probability of the xi given by xjut, the motion command that I run, times the previous belief that where the robot was. So this is the calculation of the prediction, and visually you can see what is happening over here by shifting whole this thing. So one time can be then if like robot moves to the left, then whole will be shifted to the left probabilities. If we run the from here to the right, then whole probabilities will be moved there. And based on the motion command robot is running, this will be shift and help us to make it more certain where the robot is. Now, we should see, okay, after first step of the running motion command, then how update is working. Update of the environment. We can say update by sensor or vision or whatever robot sees. So what we had in the base filter, we said that we have the belief that is updating of the predicted belief and the observation. So the observation comes from environment by sensor that I have. Of course, the sensor model that we've implemented, range bearing or something, should finally give me a probability that this probability comes times the predicted belief, the previous slide, then give me the final belief. Now I can use the same idea of the histogram filter to bring in the weights into game. So we can write it again, sum of the weighted predicted beliefs this time. So the predicted beliefs, and this term over here is going to be the weights that come from histogram filter. So how we can calculate the weights of the weights from there, looking like this term over here. So this term over here just looks a little bit complex because we have normalization over there too, otherwise nothing special, just weighted, the weighted probability of observation given by xi that shows my observation from environment times the weights that come from grid cell. Then this is over sum of all the probabilities of the weighted observation that I can have. That is normalization of the weights that we can have. So observation over this one normalized and will be replaced over the term that I have over here. So I noted some also points here that we have the, if you want to describe it in prior and posterior form, it is the prior weight. That prior weight is this term over here times the probability of the measurement that I have over sum of all that is for normalization. Prior over observation and then normalized. We don't have very complex things, just simply comes from grid cell and the terms of the base filter, and if you want to rewrite the equation, just replacing this term over there, then we have this this belief that we can write belief of the xt is equal to sum of this term times predicted belief. So that this predicted belief is the same, belief is the same, this part goes instead of base filter, normalized, observation. You see, normalized, observation. That observation is over here, and that is normalized based on the weighted that comes from histogram filter. Combination of the two things. Weights of the histogram filter plus plus the applying the base filter on the histogram filter. Yeah.
So is the histogram filter equal to the marker filter within the discrete?
This histogram filter, the idea is decompose the environment, yeah, and with decomposition show the probability of the what is happening in that region. The histogram idea is like this. Histogram filter idea is that, and we are kind of bringing that into game of the localization, kind of forming it to say where the location of the robot is with that idea, and these are showing probabilities, and where the robot is shows like more likely now my prediction says that robot is over here. After some movement with observation with the update, it will be like more likely and bigger circle, as you can see over here. So new observation comes. If the observation like robot shows over here, with the calculation of the term, the probability grows around here by updating that, then says more likely robot is here after moving. And more certain, like more movement, more certainty on the observation, and more probability come from here. So more likely, if we say observation, this observation says probability of observation time t that I am in xi. This xi, for example, can be this one. More likely I am here, more likely the probability increase. If I increase these, other ones will be decreased, right? Because some of them all should be 1. Then I'm doing localization indeed. But of course, when observation says there, or observation sees some objects that says I'm here, based on the range and bearing that I'm going to show you now. Like I'm here, I see that landmark, and I say, okay, more likely I'm here, then that probability comes and updates the whole grid cell. Then we can say we are using the Bayes filter in order to solve localization problem. Any other question? Is it clear, everything? So if you understand the whole concept, then you see that it's very easy. Just Bayes filter, change a little bit, then we have histogram filter update. So in order to understand it better, of course, we continue to give you some practices in class. This example comes from, I think I did some development myself, but also very similar. One is in Python robotics too, that you can see here. Here, this is the robot location. This is histogram filter, and this is the robot location. You should go and run it yourself today too. So the robot location is here, and robot sees this landmark. Okay. So after robot sees the landmark, why we have distribution like this, the probability of being here, more likely the robot is high after robot sees the object is like that. When I see that landmark, I haven't seen any other landmark. And more likely, I can be in circle around that landmark because I don't have any reference point. Everybody understand? So I see that landmark, everything is blank. I don't know. My probability is like maybe can be here, I can be here, I can be here, I can be here, I can rotate all around that because I don't have any reference point, and the grid cell update will looking like this. But after robot moves a little bit, update of the motion command and observation, then the robot sees like 1, 2 landmarks. And when the robot sees 1, 2 landmarks, then more likely says, okay, I should be in middle of these in grid cells because now I see that one and I see that one. Then it's impossible to be in circular form. And the concept of the updating grid cells come from there. What's any question?
It's because last assignment for Markov localization, we did it on a discrete environment, and it happens that if you discretize Markov localization, you have exactly the same.
Very similar.
Like exactly the same. So our previous assignment is exactly this.
You a little bit deviated from what we wanted then. So yeah. Okay. Then that's better. Then you can easily understand, and today is easy peasy. And the idea is like when you're doing practices, you will see in future the other algorithms you see will become very easy to understand. You will see, oh, this is like. And when you know the base of the course and the important algorithms, then new ones, whatever the complex they are, you see that with reading, oh, they changed a little bit, just the equation is changed, and they claim we did lots of like very extraordinary things after knowing the underlying concepts and algorithms. And that's the nice part of the course. Especially in reinforcement learning, we have that now. Now the students know all the simple things. Even you go to end part, you study, they will supposed to understand everything because because it's like mixture of whatever we studied. That's it. So then robot moves, sees these two, then the distribution is like that over there, and especially when you see that like the red ones has more likely where the robot is, and robot really is there, but prediction is like saying most likely is here, but there can be there too. But after seeing more landmarks, the red part is smaller, and most likely says the robot location is here, and the prediction is kind of more accurate. We've seen more landmarks. So this is happening by histogram filter localization, that you can check the code over there and the example over there. I usually give a practice or homework that I don't go to give you homework. Try with different sensor range and obstacles the example yourself. You need to download it, run it, and change the different sensor range to see what's happening when the sensors, like, because the range that we can scan the environment is limited, right? So, and it's in circular form. If you decrease it, what is happening? And if you increase it to see very large amount of environment, then what is happening? Then you're supposed to do that. And also then you need to draw the simple flowchart of histogram localization, the core, to make sure that you understand what are the steps that is happening by looking at the slides and the code together to see what's happening. So this is what you need to do. So this chapter we studied non-parametric filters, decomposition techniques, and histogram for localization. So I think you can have some time to do that. Then we have another chapter that is decomposition of the occupancy grid map, and that's also important topic, and a little bit lots of math we have again there to see. We now talked about only localization. Now based on this occupancy, like this map, if you want to construct the map, then what we need to do? Then you need to calculate everything, the range bearing, the construction and map, how can be happen, and we will see in probability form that's hard. We will bring it to log odd forms, then try to solve in mathematically, then construct the map of really where the robot is. Because after you now practicing, you will see that whatever is happening, robot is forgetting. Like after moving, seeing the object, oh, I'm here, a little bit moving far, not seeing, oh, everything is vanished. We don't have map because of that. So in next chapter we will see. So practice this. Let's see how long does it take. We may start that chapter today too. Okay, thank you. So let me share also slides with you, or you can go to Python Robotics and click on the histogram filter. You can directly have access to that one.